that means one way is to carefully reuse the data that you've been fetching already, that's in the cache of the processor. And the other thing is to use asynchronous communication, meaning that there can be some non-blocking messages flying in the machine while you do the computation. So basically, the idea is you want to try to achieve that. You take more time computing than you take communicating. So let's look at what it means. I mean, you can actually put numbers in that and see where's the limit. The flop rate, that means the rate at which you perform the arithmetic operations is, say, this number f, and take it to be 8 gigaflops per second. That would be an octaron at 2 gigahertz. I'll take the bandwidth of your machine, so that's how fast you can fetch the data from another node. Let's take it to be 8 gigabytes per second. It's a very common network today. And this is the size of the local data that you have, the local data set that you're working on. And n of s would be how many operations you have to perform on that amount of data. So suppose that you have to multiply these matrices, these data represent matrices, and you have to multiply them. That would be the amount of operations. There's 3 halves because it's the size of the matrix cubed, and if the data size is s, then the size of the matrix is s to the 1/2. So if you want to see how long it takes to compute that matrix operation, you would be n of s divided by the flop rate. But the time it takes to send or receive that matrix from somewhere else is basically the size divided by the bandwidth. And what you want is you want this computation time to be larger than the communication time. And that's what leads you to this inequality. So the problem is this is determined by your algorithm, the way the number of operations depends on the size. For instance, if you multiply matrices, the algorithm tells you this is s to the 3/2. Flop rate is given by the processor. The bandwidth is given by the network. The only thing you can change is the size of the data you're working on. Okay. So basically, you see that with the current trend in architecture, basically what happens is that the flop rate increases. They make the processors go faster by having more processors, not by making them go really faster, but having multiple cores, for instance, is one way. The bandwidth between nodes is fairly constant. It doesn't really improve. So there is a problem here, because since this is given to you, the only way to have this remain larger is to have this being superlinear, is to grow faster than s, and make this number s large. So that means that strong scaling will not be possible. Because strong scaling means you have the same problem on more nodes, and that means the data per node shrinks. Okay? So there's a kind of a fundamental problem there, that no matter what machine you use, these numbers will be roughly, will have these properties. So that scaling to larger machines for a fixed size problem will always be difficult. If I consider what happens for the n-cube problem in dynamic structure, here are just 3 possible scenarios where I consider what happens in a problem of size n, so that would be the number of electrons, and assuming that I can afford either n squared or n cubed processors, so different ways of increasing the size of the computer that I can afford. If I look at what happens with the number of operations per CPU that will have to be performed, it will go from n squared to n to order 1 if I can afford n cubed processors. The storage will remain about the same, but the storage per CPU now will become very small. That's a very bad limit. I have very little data on each CPU. So I'm done working on it immediately, and I will have to send it somewhere else right away. So strong scaling will be very hard for these problems. Yeah?
Isn't this especially a problem for molecular dynamics, since you need to look at a lot of steps, you keep your system small, and you can't, be empty depends on what happened in the last step. So
That's right. That's right. So yeah, I mean, getting longer timescales is inherently difficult and not parallelizable. You have an inherently sequential problem, and the trick of starting your simulation forward and backward in time from the same point to get a longer one, you don't get much better parallelism than that. So, yeah, that's a serious problem for ND. Just to make that worse, computer vendors don't care about us. They care about people playing video games. That's where the market is. Now, a video game, if you think about it, is a very nice parallel application. Every piece of the screen that's in front of you is a separate problem from the others, basically. There's very little information needed to draw the pixels on that part of the screen. So they can use these processors that have multiple cores, like 1,000 cores. They can do that very well. In fact, they designed those processors for that application, for video games. Scientific computing is a small part of the market. It's humbling. So we're going to have to live with that. We're going to have to live with processors that are not made for us. We're going to have to use them well. So now we have dual core chips. We have them already. We have quad core chips too. Okay, now we go to the many core GPUs. This is getting more and more difficult. We have problems of cache coherence that appear. We have to program multiple floating point units. We put compiles for that. And then we go into the more bizarre possible heterogeneous multi-core, where you have multiple cores on a chip, but they're not all the same. So you're going to have to find a way of using that cleverly. And then just to make things even more fun, you probably will have to start using different languages that are meant for parallel programming. Anyways, so there's just a view of the future that's challenging, to say the least. There's one way that's been developed, and I'll just say a few words about that, included on the practical matters. To try to improve things is to develop linear scaling methods. And this has been a subject of research in electronic structure for at least, say, about 20 years now. And the idea is to achieve order n operation for electronic structure. And you may have heard about this, I don't know if Professor Cohen's lecture was mentioning that when he was discussing short-sightedness. The idea is to basically introduce approximations in the problem that will reduce the computational cost. Now, they have to be approximations. There is no magic bullet that will transform the order n cubed in order n, simply for the fact that if mathematically your problem is an eigenvalue problem, this is known to take n cube operations. You will not solve an eigenvalue problem in less than n cube operations. So there's been a number of approaches that's been proposed, but mostly what people do is to try to represent the electronic wave functions in limited regions of space only, and that then leads to a smaller computational cost. One consequence of that is often that we have to work with non-orthogonal functions and then keep track of overlap matrices in the calculation. But most importantly, I think what's important here is try to keep the accuracy under control. So there have been a number of methods that have been demonstrated to have linear scaling behavior, but it was not always clear how much we lose accuracy when we use them. So in terms of truncated, this process of localizing the solution in finite domains does affect the accuracy of the calculation. It's not always clear how much. So I think what is really seen as an important goal today is not to demonstrate that you can have linear scaling. That has been shown in some cases. To demonstrate that you can have linear scaling and accurate at the same time. You control the accuracy in the calculation. So you want something in the end that's just as robust as your plane wave n cube method that you use every day. So this domain decomposition approach is basically based on the idea that if you represent each orbital in a separate region of space, they're all separate but overlapping, and you compute now things like the overlap matrix. You see that the cost of this calculation here will be limited because one domain overlaps only with a finite number of other domains, not all other domains. So it's going to be cheaper than in the extended wave function case. And similarly, if you compute the matrix elements of the Hamiltonian, you will have only a sparse matrix, less work to do. When you compute the energy, this will also be cheaper. So Julian and Parrinello were pioneers in that field. they started proposing methods to electronic structure and linear scaling. That's an example of some work we've done with Jean-Luc Vetter at the Lawrence Livermore Lab, where we're basically showing here what one of those functions looks like. It's a localized orbital here for a linear scaling method. That's also, by the way, in a silicon nanowire. And the sphere sort of shows you the confinement, but the amplitude of the wave function is really mostly localized in the center. I would recommend these review articles. This one is already a little bit old today, but also Stefan Gödecker did something a little bit later on review of linear scaling methods. They're good reading to understand what they are. Yes?
Can you describe methods using these?
That's a more challenging thing. Yes, you can do that, but that requires including a number of functions in each localized region that is larger. And then it's more difficult in a sense of stability than in the case of insulators. All right, so switch subject. Signal there. Okay, let me spend the rest of the lecture here to just discuss one large application. That's what we would call a large application today. That's what we could do as of basically last year. So this is an application in nanoscience that was done in collaboration with Yan Li, a very talented postdoc in this group, C. Davis. It started with the publication of this experimental work in which they were able to fabricate these crystals of nanoparticles. So there are gold nanoparticles that they managed to make in a monodispersed way, so they all have exactly the same size. They all have 102 atoms. So the way they do that is mysterious to me, but they're absolutely amazing experimental fact. They can generate that. And then they generate those things coated with some organic molecules here, which in this case are, I will show them next slide. And then they managed to crystallize these aggregates there. And they even got an X-ray diffraction characterization of that. So that was kind of the challenge then, was to try to understand, first, is that structure really what density functional theory would do? Is it stable within density functional theory? And then what's the electronic structure? So far what we had in this paper was the structural determination, but there was not much discussion about the electronic structure. So we studied the calculation of that system. So this is gold 102 and para-mercaptobenzoic acid 44. So it's coated with 44 molecules around the cluster. There are 2 of these things per unit cell. That's just unfortunate. But the crystal is such that, hey, symmetry is there's actually they're mirror image of each other. So there's just no way we can do with one of them. So we started a simulation where we actually had the whole thing in it, and that was about 1,600 atoms, about 7,000 electrons. And we had access to a Blue Gene computer at IBM in New York. We could use 4,000 CPUs there on a regular basis. This is just the parameters of the crystal. So that was the calculation. We started with 2 blocks. That's just a list. I will not go through the whole thing, but some of the statements we could make, some of the conclusions we could draw from the calculation. First of all, we would just confirm that the structure determination that they had from X-ray was stable within DFT, so we find that's an actual local minimum. We could not really run a lot of MD. That's a large system, and that was very expensive. So I wouldn't call that really an MD simulation. It was a structural optimization, if you wish. We find the usual kind of agreement we have with density functional theory for bond length and crystal geometry. So there are some details of the structure that are interesting that were noticed by the experimentalists that are nicely reproduced in the calculation. Mostly the fact that a gold cluster, when the thioadsorbates come on top of it, is sort of pulled out, one layer is pulled out of the cluster, which leads to interesting geometry at the surface. So I will not discuss more about the energetics, but that's conclusions we reached. That's some discussion about the fact that this whole cluster is actually dilated relatively in DFT relative to the experiment, which is also expected. And that's a view of these structures at the surface of the cluster. You have sort of these groups of 3 atoms that are pulled out of the cluster in connection to the thiolates that are bonded to them. That's something that seems to be described properly by DFT at the level of the PVD function. More on the geometry of these things. Now about the electronic structure, the interesting thing that happens here in the calculation is that there's actually a gap in the spectrum. So it's kind of an interesting finding here. If you look at just a gold cluster, that would be the red curve here, just a gold cluster of the same number of atoms, 102 atoms. You don't have a gap. It stays all over here. And if you now coat it with these organic molecules, it manages to open a gap in the spectrum. You have about a half EV gap within DFT. So usually density functional theory will underestimate gaps. We know that from all the system. So we can sort of say with some confidence that there should be a gap in that system. So this whole assembly of coated gold clusters is actually a semiconductor. That's our prediction anyways. If we look at now what the electronic states look like, we can do things like look at the valence spin maximum and the HOMO state and the LUMO. We find that basically they are mostly located on these clusters. Same for the LUMO. So that's sort of confirming the idea that we could just study one of them. We didn't really need to, if we're just interested in HOMO LUMO, we didn't really need to do this whole thing. If just one isolated cluster would have been okay, but we had to make sure that there was no amplitude of the wave functions in between to be able to do that. Maybe I'll skip that for a discussion of how this band gap depends on how many molecules are absorbed on the cluster. Something that we can get from that.
Can you please tell why DFT always underestimate the gap?
Oh, why it does is very unclear. There's no simple proof that it should always underestimate gaps. I think it's an observation that in all the systems we know, I think semiconductors at least, density functional theory, I shouldn't say density functional theory, the local density approximation or the GGA does underestimate gaps.
Yeah, because in every paper they say, but no clue is usually given. Why? It is
Well, I guess you can sort of understand it if you try to compare. You compare the local density approximation to other schemes such as GW and try to identify related terms in self-energy. You can sort of understand why that is the case, but I don't think there's proof that local density approximation will always underestimate gaps. I think it's just an observation. So another interesting thing that we did in this calculation there was to compute maximally localized one-year function. So here I'm just a little bit skipping ahead because I understand that on Friday you're going to have a lecture on one-year functions. These are basically linear combination of the wave functions that minimize the spread of the wave functions. So it's a representation of the electronic structure with wave functions that are as localized as possible. And we did this calculation in the system. So it's about 3,400 one-year functions, since we have about twice that number of electrons. And the interesting thing that happens here is that it's a bit unusual in what we've done so far, is that there are two classes of one-year functions in the system. And there are one-year functions that are well localized on all these organic molecules that are coating the cluster. But then inside the cluster, there are one-year functions that are fairly delocalized. And what's more interesting is that these delocalized wave functions, and let me explain a little bit more here what these plots mean. This is first a plot that just tells you what the geometry of the cluster is in terms of number of atoms as a function of the distance from the center of the cluster. So these are just a histogram that shows you where the atoms are. I compare that to the spread of the wave functions, these one-year functions. So the spread large, meaning those are very delocalized, and these are very localized. So we have a bunch of fairly localized wave functions here in the core of the gold cluster that correspond to the d electrons that are on the gold atoms. But we also have a smaller number of completely delocalized wave functions. So we have two classes of one-year functions here that are distinct. And the interesting fact is that these wave functions here, there are 29 of them, corresponding to 58 electrons. And 58 electrons turns out to be what they call a magic number in the studies of metallic clusters. This is the number of electrons that would form a closed shell if you just had a spherical system. So if you had a spherical jelly and 58 electrons, you would have a gap. So this turns out to be the case in this system, and well, this is more of the same discussion. So that was kind of information on the electronic structure that would support the idea that these clusters with 102 atoms encoded with these molecules are especially stable because they have this magic number of electrons. They have a closed shell of electrons in the core of these clusters. So this is supporting some theories that were made by the experimentalists because they were trying to find out why is it that we have been able to synthesize this with this particular number of atoms. And that argument would support the idea that the magic number of electrons here is particularly stable. Anyway, so this is just to summarize the kind of thing.
Is there any practical interest of this? Because usual gold particle coated with iron for cancer treatment and so on. But what is the practical interest?
I think at this point they don't really talk yet about practical applications of that. I think the fact that they could manipulate that. In fact, I think there's a lot of interest in this system because it's, I think, the first time that we can study a coated gold surface with thiol adsorbates where we know exactly the geometry of the gold. There's been lots of studies on surfaces with self-assembled monolayers, and there's always some discussion about what the exact structure of the surface is, what the exact structure of the gold is. And here they have X-ray crystallography that really tells you exactly where every atom is. So we have a sort of a reference system where we understand the geometry. So this by itself is interesting, but we're not talking about applications.
Because nowadays many papers are coming on plasmonic application of gold coated with dielectrics and stuff.
Well, that, I guess maybe one day, but I haven't heard yet of applications of this. So, okay, I guess I'll conclude with just that. I mean, those kind of conclusions we can draw, which is a typical thing about the structure and the electronic properties that we get when we test the functional calculation. But I was just using that to illustrate that this is basically the limit where we are now. It's these systems of maybe 7,000 electrons is pretty much the limit of what we can do with a large supercomputer.